In the last video, we started looking at conformations of cyclic alkanes. So we said oftentimes to relieve strain, they're going to adopt a non-planar geometry. And I want to spend more time specifically on cyclohexanes in this video. So remember our cyclohexanes, they do have a lot of torsional strain, and I'm not going to draw the hydrogens or the bonds on right now, but each of those carbons would have two more bonds. And in the planar conformation, right, where all of those carbons are in one plane, there's a lot of torsional strain. We also said that it has angle strain. My bond angles are 120 degrees, so this has both torsional and angle strain, also known as ring strain. Right? Remember, angle or ring strain is if we take the bond angle and we expand it or compress it beyond what it wants. So in this case, all of those carbons are sp3 hybridized. They want to be tetrahedral, so they want to have 109.5 degree bond angles. In my planar version, they're actually 120 degree bond angles. Right? It wants to be 109.5. So I do have angle strain in addition to that torsional strain. So what we did is we said that this is going to form a chair conformation. So I'm going to take one of the carbons and move it up. I'm going to take the carbon directly across from it and I'm going to move it down. So the four that I didn't mark in blue are still in the plane. And then I have one carbon going up and one carbon going down. By doing that, I'm relieving torsional strain and I'm also relieving angle strain. When we looked at cyclobutane and cyclopentane, when I adopted my non-planar geometry, I actually made the angle strain worse, right? I made those bond angles tighter, and they were too tight to begin with. Here, my bond angles are actually too big to begin with, right? I want them to be smaller. So I'm actually relieving both torsional and angle strain when I do this. So it alleviates both torsional and angle strain, right? We want to increase the angle on those a little bit because it's too big. We also went and said that we have two different positions. So we have our axial positions, which I'm drawing in pink. I'm going to put a little AX on them. And they're alternating. So on the carbon that's up, my axial position's up. On the carbon that's down, right, this one that I just drew the line on, my axial position's down. And then these guys, I do those kind of close to each other, are alternating every other as they go around. So axial's up on the carbon that's up, down on the carbon that's down, every other carbons are up, down. And then my other positions were equatorial positions. The carbon that has the axial up is going to have the equatorial down. And it's not straight down, it is slanted. And they're going out around the middle. So EQ for my equatorial positions. Keep writing those EQs backwards. It's a habit because usually when I'm bonding them to carbon, when I'm on this side, I would write it as CH3 because I want it to go to carbon. And then when I'm on this side, I write it this way. So it's kind of funny. I'm just in that habit of writing them backwards. So we're just going to go with it. So EQ, equatorial, and then my pink ones, AX, those were my axial positions. I'm going to redraw it, just putting the axial positions on there. So we're going to draw our chair again. And I'm just going to look at axial positions. So up, down, up, and then this actually like goes down. And remember the bonds that are eclipsing, it doesn't matter what's attached to them. So if I have a hydrogen on those bonds or if I have a methyl group on those bonds, it doesn't matter, right? I still have eclipsing bonds. And then we said we could add torsional strain, or sorry, steric strain, if I was to substitute those hydrogens for larger groups. So if I was to go and put a CH3 group on here, and I'm actually going to draw it out structurally to help make my point. And then I'm going to stick one here. Those guys can get pretty close to each other, right? If I was to put one, I'll just put a dot. But if I was to put one here, it's just as close to this one and this one that I circled as the two that I circled are to each other. And then and the same thing on the bottom, right? If I was to put one here and one here, those guys are pretty close, or one here, it's just as close. It doesn't really look like it in my picture, but they are equidistant. So what kind of strain do I have between those groups when I add them? Yeah, steric. Good. Remember, steric strain is when I have groups of atoms, right, that are just too close to each other, right? Remember, it's all electrons, bonds are all right? Bonds are all electrons, it's all negative charge. So I have like a whole lot of negative charge right here and a whole lot of negative charge right here, and they're just awfully close to each other. So that's going to be my steric strain. If I was to do the same thing, didn't write the rest of the word. If I was to draw my chair conformation, and we can look at the same carbon. Actually, I'm gonna pick two different ones, so I want them to be going up. I'm gonna look at the equatorial positions, but equatorial is down on this one. So I'm gonna pick this carbon, and it doesn't matter. I just want to be able to make comparisons to the one on the top, and I think it's gonna be easier. This one's gonna be down, right? Because they alternate. So then this is my other one that's going to be up. So on this one, I picked two axial that are up. Here I'm going to pick two equatorial that are up. And I'm going to put methyl groups on those also. But because these are equatorial, and we'll get the models out here in a few moments, but again, remember my equatorial positions are pointing out around the outside. I did inadvertently say middle towards the end of the last video when I was showing the model. The equatorials are pointing to the outside, right, not the middle. And because of that, I don't have that steric strain. So I have less steric strain when my larger groups are in the equatorial position. When those larger groups are in the axial position, I have more steric strain. There's a specific name for that. It's called a 1,3 diaxial interaction. So diaxial because it's between two axial groups. And then 1,3 is just the relationship between those carbons, like not numbering it for naming it, just numbering it. So if this was carbon 1, this would be carbon 2, and this would be carbon 3. So between the group on carbon 1 and the group on carbon 3, they're both axial, so diaxial, I have steric strain. And if I was to put that group here instead, I'm just going to do CH3 because I'm just going to run out of room, but it's the same thing. It's still 1 and 3. So if I want to make this carbon 1, this carbon 2, and this carbon 3, between the groups on those carbons, I have steric strain. And we could do the same thing if we did it on our bottom carbons. If I was to put a group here, and a group here, and then I was to number those, this is carbon 1, this is carbon 2, and this is carbon 3, so my groups on carbon 1 and 3 have steric strain between them. So 1,3 diaxial interactions we want to avoid. We don't like having a molecule where I have large groups in that position. Now again, if it's just hydrogen, I'm not worried about it, right? If I just have hydrogens here, remember hydrogens are just a little 1s orbital. It's tiny, right? And hydrogens aren't bonded to something else other than the carbons they're attached to, so there's nothing sticking out to get in each other's way. So I'm not worried about hydrogens. We're just worried about larger groups. Like even a fluorine's not that big, right? Fluorine, it's a 2s or a 2p orbital. But if I had a bromine there, bromines are getting pretty big. Iodine's huge. So usually alkyl groups and then anything else that's big, we want to avoid putting in the axial position. So kind of as a general rule, more stable molecules, and by molecules I'm talking specifically cyclohexanes, will have larger groups in the equatorial position. We want to avoid 1,3 diaxial interactions, right? To avoid steric strain. Our 1,3 diaxial interactions. And again, by larger, I'm talking alkyl groups, so carbon-based substituents, right? Because those carbons are then bonded to things. Or, you know, chlorine's getting kind of big, but generally like bromine, iodine, bigger groups, things that have lots of electrons that can have steric strain with neighboring electron groups. If I put them in my equatorial positions, they're going out around the middle and you're avoiding that. So a model of that, I'm just going to start with my plane without anything on it, my plain cyclohexane. And then I have two methyl groups and I'm going to put them in the 1 and 3 position. So 1 and 3 from each other, however I hold it, 1, 2, and 3. And then I'm going to put this in a chair conformation. And I'm going to put it in the conformation first. That puts them in the axial position. And if we look, you can see how close those groups are, right? They're both going up. If I want to have them both going down, if I want to rotate it so they're in different positions, however you want to look at it, they're carbon 1, 2, 3, so 1 and 3, and they're both axial, so diaxial, and they're awfully close to each other, right? Even if I just had a hydrogen, I'm out of white atoms, but pretend the green is my hydrogen, those still have some steric strain, right? It doesn't have to be two methyl groups. If I have a larger alkyl group, and a methyl's as small of an alkyl group as we can get, right? It gets much bigger. If I put an ethyl group on there or something like isopropyl, it gets big. I'm going to have steric strain between that group and the axial position that's on the third carbon from it. So if this is carbon 1, carbon 2, carbon 3, I have that 1,3 diaxial interaction. If I was to then take those groups and change it so that they're in my equatorial position, sorry, it just takes a little bit to move it, they are now going out to the side. So let me get my chair here correct. Right? Instead of going straight up now, you can see how they're going out. Whatever version you want to look at it, they are now not causing strain, right? And if I had a hydrogen there instead of the other methyl group, I certainly don't have any steric strain. So putting those larger groups in the equatorial position is going to relieve steric strain between it and whatever is 3 carbons away or 2 carbons away, right, in the third position. I want to go through a couple examples where I give us a structure and then we're going to draw it in its most stable chair conformation. So our first one, we're going to draw Tbutyl cyclohexane in its most stable chair conformation. And I think this is something I might have forgot to tell you before. Tbutyl is Tbutyl. It's just a shorthand way, and you guys can totally use it, of writing Tbutyl. Remember we had those special alkyl groups. So we had isopropyl, isobutyl, sec-butyl, and tert-butyl. So Tbutyl is tert-butyl. Those are the same thing. And then for the sec-butyl, you could actually write S-butyl. It's a lowercase s, a lowercase t. Make sure they're lowercase. If you want to write sec-butyl or S-butyl, that's perfectly acceptable. So if you want, again, if you want to save yourself some letters, put T for tert, put S for sec. Again, remembering we do alphabetize those based on the B. So side note for us. So I'm just going to draw it planar first, just to make sure we can draw it. So cyclohexane, I have a ring of 6, and I'm just drawing it flat. And then that Tbutyl group, that was the one where I go out to a carbon, and then that carbon branches to 3 other carbons. Because I just have one substituent on this cyclic structure, I didn't have to say where it is. Right? Remember, if we have one group, it's always going to be on carbon 1, because for naming, right, we always need the lowest number for our substituents, which means if I have one substituent, the lowest number is always going to be 1. So I could say 1 tert-butyl cyclohexane if I wanted, or I could say tert-butyl cyclohexane, or those two things replacing tert with T. So this is my structure. I'm going to just draw my generic chair without anything on it, so I have my chair. And then we need to remember, I'm going to draw another chair, that these positions matter. So I can make any carbon, carbon 1. I can make, right, it's a ring. So if I want to make this carbon 1 and go counterclockwise, I can. If I want to make this carbon 1, sorry, if I want to make this carbon 1 and go clockwise, I can. It doesn't matter. It's your structure. It has one group on it. Make one carbon 1, whatever you want. The part that does matter is that how you angle them is important. Remember, on the carbon that is going up, if you're going to put it up, it has to be axial. If you're going to angle it down, it has to be equatorial. Right? If you were to draw that chair, that's the ugliest chair ever, and you were to do that, that is not an acceptable position on that carbon, right? These two that I just drew are the only acceptable positions. So you can make whatever carbon, carbon number 1, you just need to make sure that whatever you do, you're putting them in the right position. So kind of often when I'm learning, this just has one group, so it's not that hard, but I would just go and I would stick your, like, kind of in the margin or on a piece of scrap paper, draw all of your positions. So remember, the axial is up on the carbon that's up, and that's where I always start, and then it alternates. So that was up, down, up, down, up, down. And then your equatorial positions are the opposite. Down, up, down, up, down, up. Those are the only places you can put atoms, right? If you make a bond that's different than those, you're actually making it incorrect. So I want to make my most stable. So if I want to make my most stable, do I want to put that group in the axial or the equatorial position? Yeah, good, equatorial, right? We just said that. More stable molecules have the larger groups in the equatorial position because we're avoiding steric strain between it and whatever is on carbon 3. So I want that tert-butyl group to be equatorial, which means if I'm going to pick this carbon that's going up to be carbon 1, then I need to draw that tert-butyl group like that. Essentially, I'm going to go back and erase all the purple ones. You can put your tert-butyl group in any of those blue positions and you're going to be correct. I tend to pick the carbon that's up as carbon 1, but if you wanted to make this carbon 1, that's fine. You just need to make sure that that's how you draw it, right? This is the accepted position. So I'm going to draw a chair conformation. I only have one group on there, so I can make any carbon, carbon 1. I want that group to be in the equatorial position. And these are the allowable equatorial positions. So any of those spots, you can put that tert-butyl group and you would be correct. Another example, and this one's a little trickier. We're going to draw cis 1,2-dimethyl cyclohexane in a chair conformation. So I'm not going to specify more or less stable on this one. We're just going to take this molecule, we're going to draw it in a chair conformation. I'm going to draw it planar again, just to start with. And you don't necessarily have to do this. You can go right to the chair. It's just that we're still learning how to draw them, so I'm going to do that first. So I have 6 carbons in a ring, right, cyclohexane. Dimethyl, meaning I have 2 1-carbon groups, and they're on carbon 1 and 2 from each other. And you can make, it doesn't matter, because again, it's a ring, you can make any of those carbons 1 and 2. So I'm going to choose to make that 1 and 2, but if you wanted to make this 1 and 2, it really doesn't matter. They just have to be adjacent to each other, right? It's not 1 and 3, it's 1 and 2, so they're next door. The other piece of information we're given is their cis. So remember, cis was one of our type, right? Cis trans were our stereoisomers. So cis meant those groups are on the same side of the molecule. So when I draw this planar, I'm going to either have them both coming up or I'm both going back. So both wedged or both dashed. It doesn't matter which, I just need to have them on the same side. If I was to draw this planar, right, how we've been doing it in this set of videos, right? If I wanted to draw it that way, where my ring is coming in and out, and again, it doesn't matter which 2 you make, the 1 and 2, I'm going to take the 2 on the top because I think it's going to be easier to draw. I'm going to draw those both going up, right? Same side. If I wanted to put them here, that's fine. I just need to have them both going up. So remember, cis means they're on the same side of the molecule. Since I'm drawing skeletal structures, you don't have to write CH3, but sometimes it's easier to see it that way, right? Same side is what cis means. So be really careful. I'm going to show you what people do wrong in a minute. Like right now that makes sense. You're like, yeah, Jen, why are you beating this to death? We know cis means they're on the same side. This is where folks go wrong. So I'm going to draw my chair, and I'm just going to draw, whenever I draw my little key, I always draw it too fast. So I'm doing the one where I put those positions alternating. So axial, up, down, up, down, up, down. Equatorial, down, up, down, up, down, up. And again, this isn't my answer. This is like my little roadmap, right? Or my key. These are the positions that I can put my groups in. So now to draw my structure. And again, you can make whatever groups carbon 1 and 2 you want. I'm in the habit of making this carbon 1, the one that's up, and then I like to go clockwise, so I'm going to make this carbon 2. Again, you can make, as long as they're adjacent, you can make any of those carbons 1 and 2. So if I'm going to make those 1 and 2, and I look at my key that's in the box there, since I want cis, and I'm just going to put the first one on because it's going to be easier to ask you what I want to ask you. So I'm going to put my first one here. Does the 1 on carbon 2 go in the axial or the equatorial position? What do you guys think? When I go and stick it on this carbon, if I want cis, and I drew this one axial, right? That's axial, it's straight up. Do I want the 1 on carbon 2 axial or equatorial? I actually wanted equatorial, and if you said that, great. If you said axial, I get why you're saying that, because most people that are learning it do, right? They think, well, since one is axial, the other also needs to be axial, but that is not what cis means, right? Cis means on the same side of the ring. So what I need is the two that are going up, right? This is where I put my first one. Since it's going up, I need my second one to also go up. If I would have put that in this position, I would have drawn trans because it would be going down. So be really careful. When we're taking cis and trans and applying it to the chair, it doesn't mean they're both axial or both equatorial for cis and one axial and one equatorial for trans. That is not what it means. It still means they're on the same side of the ring or they're on opposite sides of the ring. So just be careful. Since I drew my first one up, I want my second one also up. If I would have chose, because remember cis, they can both be up or they can both be down, right? If I wanted to go back to this original, if I wanted to draw this down, I would draw this one down, right? There's still cis, they're on the same side. So if I wanted to draw this chair, and I'm still going to use the same carbons as 1 and 2, but let's say I put my first group here. Since that's down, my second one is now going to be axial because it also needs to be down. So again, cis and trans, cis means they're on the same side of the ring, trans means they're on opposite sides of the ring. So cis 1,2 dimethyl cyclohexane has one of those groups in the axial position, the other one's in the equatorial position. No matter which two carbons I picked, right, even if I look at this one, that's how they're going to be. If we do another one, let's do cis 1,3 dimethyl cyclohexane. So this time those groups are going to be on carbon 1 and 3. They're cis, so I still want them on the same side of the ring. And I'm actually going to draw it up here so I don't have to redraw my key. So let me get these things out of the way. And then I'm going to draw my chair. And then I'm going to use this carbon as carbon 1 again, because that's what I usually do, which means this is going to be carbon 2, and then this is going to be carbon 3. And again, you can start wherever you want. You don't have to do it how I do it. It looks like it's the one that's up. So when I go and make my little up-down map, it's the one I always start on. So I tend to start on that carbon. So 1 and 3 is where I'm going to put those groups. We are drawing cis again. Remember, cis means they're on the same side of the ring. So if I wanted to put my first group here, I drew that up, right? I put that in this position right here. So on carbon 3, the one that's also going up is going to be axial. So I am going to put that group here. I'm going to draw that again. This time I'm going to choose to put my first group still on the same carbon, but I'm going to choose to put it in that equatorial position, which means because it's down now, when I go and draw the one on carbon 3, it also needs to be down, which is going to be equatorial. Which one of those two do we like better? If I said draw the more stable one, which one are we going to draw? The first one I did with the groups in the axial position, or the second one I drew with the groups in the equatorial position? Yeah, good, the equatorial, right? This one is going to be more stable. Right, we're avoiding 1,3 diaxial interactions, right? There's steric strain between this group and this group. By putting them in those axial positions, I've relieved that strain. If I go and look at, oh no, they're right here. If I look at these two, right, my cis 1, 2, they're equal, right? If I look at this one here, I have one axial and one equatorial, and they're both methyl groups. If one was a methyl and one's an ethyl, now there's going to be a difference, but they're the same group. And then if I look at this one, I still have one axial and one equatorial, so these are going to have the same energy. right? They're equally stable. But my 1,3, which I've answered up here, sorry for the mess, guys, I just wanted it to be next to this. Those are not equally stable because this first one that I drew with my groups in the axial position has steric strain, where this one has much less steric strain.